You can define also air ventilation, because in the mold can be also air ventilation, and of course the warp boundary and the injection location. Okay, so let's now switch to the results. Again, I will start from flow results. Here, of course, we can reanalyze the flow, the filling. Why? Because in this case we have a solid mesh, so it's far more precise and detailed. So in this case, I can show you the same results of before, but more smooth. But also it's nice because I can see inside the mesh, because it's solid. So when I use this representation, you can see inside. So this is the effect of using a solid mesh instead of a shell one. Okay, and it's far more evident also where are forming the weld lines, for example, here. Okay. Also, of course, I can review all the results that we saw earlier. From the cooling point of view, what you want to evaluate, for example, you want to evaluate the final temperature, the cooling time, and the final temperature of the plastic part. So again, here you can see in those areas, maybe there are some temperature remaining. You can see also here temperature at the end of the cooling. So you can evaluate here the difference from portion to portion. Also, because of the solid mesh, you can see inside in a clipping, let's say, behavior. For example, also we can change the location of the clipping, like in this way. So you can see inside what's going on. So okay, from let's say surface point of view, it's cool, but maybe there are some points, some areas that are needed to be cooled after the ejection, maybe. So it's a matter of understanding what is going on. And of course, from temperature point of view, you have to know if this temperature is above glass transition or not, if it's already a solid or not. Okay, also from a cooling point of view, of course you are interested also to see the reaction on the cooling system. So for example, you can see the average temperature, but also it's interesting the heat flux here. So the heat flux is representing the temperature that is coming out, the energy that is coming out from the cooling system. So it's a matter of measuring the efficiency of the cooling system. There are far more joules of course, from the baffler, because it's inside, it's very near to the cavity, instead of those cooling channels here. And maybe you can optimize the dimension. Maybe it's not needed 10 millimeters, you can try with 8. Then we can see also the warpage, the final deformation after the ejection. So when you are opening the mold, there are two main aspects. One is the pressure that is remaining inside the cavity, and the other one is about the temperature, the different temperature inside the cavity. Time when you are opening the mold, there is a thermal shock. And in this case, you can see the total stress displacement. So you can see, you can evaluate which is the final deformation. Of course, in this case, I have a scale of 1. And if you want, you can enhance the scale to see really what's going on. So this is distorted graphically, but to show you what is going on. So for example, this portion will rise up while this is going down. And also you can see the value. So we are here, we are about 1 millimeter of deformation. Okay. Also you can see, for example, in different direction. For example, I want to see only in X direction, only in shrinking in this direction. So I can evaluate that is shrinking here or here by 0.8. Or of course I can also measure. So I can point here and here. I can see that the final deformation is 0.2 from 0.1 and 0.2. Okay. So I can evaluate all these kind of deformation as well. Okay, of course here I can see the I can see the first let's say the singular stress displacement residual, for example, from pressure point of view, as I told you, so in mold residual stress and quenching thermal stress. Okay. Another thing that is really important here to see again the sink mark profile, because the sink marks are calculated also in the filling phase and in packing, but here are far more precise, so you can see the final value. So here you can evaluate better which are the final area of problems from sink marks point of view. Let's say briefly. From plastics premium point of view, it's basically focused on mold designer, mold manufacturers. Okay, let's finish this webinar about plastics validation. This is nice. This is nice work done by the UMass University in Massachusetts, by the Professor Stephen Johnston, the UMass Lowell of the University of Massachusetts, and they have helped us to understand how can be precise our software towards the real scenario. So they have done injection and they have done virtual simulations in basically these three parts. So also with a mesh, a solid mesh, and the runner system. Let's check it quickly. The radon detector is polypropylene, it's a family mold, imbalanced, and there is a cooling system. From cooling point of view, you can see the actual test sensors, measures, location, and the simulation. You can see that the final value are really near to the virtual simulation test. Also from the filling point of view, we have with the machine it's very easy to select a filling time to see at that time which is the filled part and then eject it. And in the software again it's very simple because you can stop the simulation or you can stop the results at that time. So from filling time point of view, you can see that they are very, very similar to the final part. So again, this is 1.48 and 1.4 in the simulation. This is more advanced. You can see also here in the rib section, it's very similar to the final part. This is the gate imbalance. So also the gate imbalance here, like we saw with the demonstration, can produce hesitation mark. It's not a short shot, but it's a hesitation. Hesitation means that the plastics is really slowing down and can produce this kind of problems in the final plastic part. And you can see that the software is going to show you that there is an hesitation in the animation. Okay, this is the filling. This is the final results and the flow rate set point in the machine. Again, also for the pressure, this is the maximum test is it's 50 megapascals and the simulation is going to have 48, so it's very similar to the simulation. The packing, again, the plot temperature are set in near the gates and very similar to the profile that we saw earlier with the demonstration. Also from gate freezing time, the simulation is predicting 6 seconds and the test they are saying 6 seconds. So very similar to the simulation. And from the warping point of view, the shrinkage of the part, the final shrinkage in the actual part is about 1 millimeter, and in the simulation is 0.9, and you can see from the photo the very same deflection. So very similar to the warpage that is predicted inside the simulation. You can see here, and you can see here the very same behavior. This is a medical cap. I will go very fast forward here because we are short in time. I'm sorry. So again here there are some sensors very similar to the simulation. So the tests are here and the simulation. Again the shot series, so you can see the final results on the actual part and the simulation. And the packing, of course. So also in here the experimental phase it's pointing 5-6 seconds of ideal packing, and the simulation it's very similar. Electronic housing, again here the cooling, the temperature is very similar results. Shot series. If you want also you can download this from the webinar panel, this document, or I will send to you, it's not a problem. Also here it's very interesting to see the final issue with the weld line. The weld line is producing a structural weakness, not only a defect, an apparent defect, but also a structural weakness. Here you can see also the final part is breaking. Again, the packing is very similar, the shrinkage, you can see the test, and so on. So this is nice also to have some virtual simulation comparing to experimental data. Just to finish the presentation, I will point out the value of virtual simulation. Let me go straight to the point. This is an Aberdeen report in 2014, but still valid. And the final takeout, it's about the features that are important to the designer. And you can see the first one is not the accuracy, that of course it's important, but the first one is the integration with the CAD environment. And the fourth one is the easiness. So the software has to be easy to use. And again, which are the benefits for the companies? The companies that are using actually virtual simulation, you can see from these graphs, are far more advanced, are far more, let's say, successful from quality targets point of view, product revenue targets point of view, launch dates, so time to market, and of course cost. So to finish this webinar, I would like to show you the references. So you can email me directly, you can go to the LinkedIn profile. Also, I would like to share with you the what I have done in the past. Some other webinars are recorded and put on YouTube in my channel. So also this webinar, it's recorded right now, and in some days you will see the link, and maybe next month I will put it in YouTube.